nice, beautiful night, a lone traveler stands on their ship and they look into the void. They jump, cut off their jetpack, and they fall. To the untrained eye, there's absolute madness. But to us, no. This is science. Join me as we answer the question, how fast do you really fall in No Man's Sky? Gravity, one of the greatest discoveries of all time. From a single apple hitting the head of Sir Isaac Newton, a whole world opened up. We got planes, rockets, space shuttles, and planetary motion, all at our fingertips because of one apple and one man who said one word: gravity. And so I think it would be a great disservice to a space game like No Man's Sky if that same world was not explored. And so today, I have set out to find the acceleration due to gravity, also known as little g, for planets in No Man's Sky. Is this some great scientific endeavor? No. Are there going to be so many errors and uncertainties? Yes. But is that going to stop us from following the footsteps of one of the greatest? The GOATs? Isaac Newton himself? Definitely not. So the plan is simple. Step 1. Find a planet. I'll try to make sure I find planets that are very different, that is in weather, the size, climate, animals, I don't know. Anything that makes them different. Step 2. I will enter the atmosphere of the planet. I will park my Corvette in the sky. Step 3. I'm gonna make an end and starting point to measure the jump distance from my Corvette. Step 4. Jump and repeat. This is gonna be the easy part. Step 5. I'm going to record the time in DaVinci Resolve. Step 6. I'm going to put all the data that I get into Microsoft Excel, one of the greatest things that ever happened to mankind. Alright, now that we know what we're doing, let's go to our first planet. Planet number 1, Zomitao, a highly radioactive planet. This is off to a great start, ain't it? Now the ego item on you would have noticed that I already have a base computer on this planet, meaning I've already been to this planet. Funny story actually. I already did all this jumping process before, but then I forgot to record it in OBS, so this is actually my second try. 2 full hours of hard work just gone. The second time's a charm, right? Isn't that what they say? Alright, let's move on to step 2 and pack the Corvette. Now the thing about the next step is that I actually have to do a test jump first to know where I'm going to land. So, here goes nothing. After falling for some time and finding my landing spot, we move to step 3, defining a starting and end point. Now I did this by building a platform which had 2 parts, the main one for landing and a little one to serve as a final marker in DaVinci Resolve when I go to get the time. Now to get the actual distance measurement, we have a bit of a problem. I can't seem to measure vertical distances directly. My plan to solve this was to find a spot close to the same elevation and then subtract 10 to 15 units for margin of error. So I think it is at this point I should say the units that we're using for the distance measurements are units, no pun intended. 1 unit is to 1 meter. I found this on the internet, and who am I to doubt whatever is online? Alright, so now that I'm actually editing this video, I realized I could have just used good old Pythagoras, because I know the hypotenuse, that would be whatever distance that I get because I can't measure directly, and then I could have just found some angles, done some magical mathematical stuff, and then I would have gotten the vertical distance. But hey, that is done now. So Using the 600 meters as our first distance, this was of course after subtracting 10 meters. We're set to go. So now we go to the fun part, jumping. I did 5 jumps for this planet. That is, jump from the Corvette onto the platform, go back into the Corvette, jump 5 times. And I think that's enough trials for this planet. So we move on to the next ones. Alright, so here are the rest of the planets that I went to. Second one was Pointoneb Alpha, a Hyperborean planet. It had a lot of ice and it was very cold. The third one was Nojo 75/U4. This was a torrid planet which had dinosaur bones and a lot of lightning storms. The fourth planet was noman'ssky, or bountiful planet. And from the name, it definitely did not lie. It was a bountiful planet. For the last planet, the sixth one, I picked Rihoni E24, a blood planet. Yeah, spooky. I didn't see any blood though. I have no idea why it's called that. Any No Man's Sky experts in the chat? Put in the comments why it's called a blood planet. Now, we're going to be finding the time in DaVinci Resolve. So we'll put a marker directly when we leave the platform, and then a final marker when we get inside of the little platform that I put for the landing site. That should be able to give us the full time in the upper left corner. Should be in hours, minutes, seconds, and frames. Yes, frames. Stay with me here. So since the video was recorded at 60 FPS, we have to divide the last number, that is what shows there, the frames, by 60 to convert it to seconds. So I'm not going to go through the video in Resolve, find all the 25 trials that I did for each planet. So that's 25 fall times and then 5 fall distances for each planet. Fun stuff. These are the results that I got from DaVinci Resolve after going through the video. So I got the distances and the times for each planet. So as you can see in this document, we have the planet, trial, approximate fall distance, approximate fall time, and the acceleration due to gravity, which we haven't gotten to yet. That's what we're going to be calculating. So as you can see, Azometao, I was 600 meters parked in the air, and that took approximately 21.2 seconds. And then we go to Pointoneb Alpha, that was 300 meters, that was 10.92 seconds, which is almost half of Azometao, which was 600 meters high, right? And then you go to Nojo 75/U4, that was 127 meters in the air, that was 4.797 seconds. noman'ssky, which was 300 meters, 0.9, parked in the sky, that was 10.56 seconds. And the last one, Rihoni E24, I was 448 meters in the sky, and that took 15.41 seconds. So already you can see that there's some kind of relationship, right? Because for Azometao and Pointoneb Alpha was half the distance, it got almost half the time. So there's some relation there. So I don't know how the acceleration due to gravity is going to come out. We're going to find out after we calculate it. And that's where we're going next. To calculate the acceleration due to gravity, we're going to be using Newton's equation of motion for freefall, specifically the one that relates distance, initial velocity, time, acceleration due to gravity. So as you can see, we have y equals u subscript 0 t plus g t squared over 2. So y is the change in distance, or the total distance. U subscript 0 is the initial velocity, t is the time, and g is what we're trying to find, little g. Now since we didn't have any initial velocity, we just stepped off the Corvette. We just take initial velocity to be 0. So then u subscript 0 t is going to be 0. So then that just goes away. So then we just have y equals gt squared over 2. And from this, we can make little g the subject and get 2y over t squared. And we have our formula. So we're going to be multiplying the distance by 2 divided by the time squared. Now this is exactly why I got the time from DaVinci Resolve instead of just using like a timer or a stopwatch to get a time. So you see here the time is squared. So any little miscalculation, any wrong input is going to be squared. So the more error that you have in getting the time, the more error you're going to have in the final answer for the acceleration due to gravity. And I try to minimize that by using DaVinci Resolve. Alright, so we're going to go ahead and put that into Excel and see the values that we get. I mean, this is the whole point of the video. So, and now for the review. These are the G values that I got from the calculation. And at first glance, they look reasonable, right? Well, not quite. If you look at our time and distance for each of the planets, we can see the relationship that I mentioned earlier, right? But now for the gravity, for Nobunka V and Pointonev Alpha, they had almost the same fall distance, and you can also see that they had almost the same time. And when you go to the gravity side, they have pretty much the same gravity at 5 point something. Now let's say the discrepancy between the 5 is due to the error in my calculation, right? They basically have the same acceleration due to gravity. And how is this possible? Because these planets are in different systems. They have different weather patterns, they have different climate, everything is supposed to be different. Even the acceleration due to gravity should be different. So why? Well, I made a graph of the fall distance versus the fall time for all the planets. And what I found is very interesting. The results were shocking. There was almost a linear relationship. The graph had an R-square value of 0.998, which is very good. As close as it can be to 1. If it's 1, it means it's a perfect relationship. So that is very high. And so we can say that the correlation is very strong. Well, this shouldn't be bad, right? But it is. From the formula that we use, the distance is related to the square of the time. So, a graph of distance versus time should be a parabola, aka the little smiley face graph thing. But instead we have a straight line, which is not what we should be getting here. So something is definitely wrong somewhere. So, I decided to check the fall velocities of the planet. That is just distance over time. And this is where it gets weirder. It gets more interesting. They had the same fall velocities, each and every planet. Like, what? This doesn't make sense. This is blowing my mind right now. So every planet in No Man's Sky, right, apparently has the same fall velocity. Now this is crazy. So it means there is no acceleration whatsoever, and the only thing that you're falling with is a constant velocity from wherever place that you jump from, whatever distance that you jump from, wherever you start from. So I guess this is just like the game engine just sets a constant velocity for every planet, and this is insane. Now I know we set out to find the acceleration due to gravity, but we found something else. We found your fall velocity, and it looks like regardless of your initial velocity, you're going to fall at a constant rate of 28 meters per second or 28 units per second. Well, this is a rough estimate. It could be like 26, could be 30, plus or minus, let's say 2. Yeah, just for a margin of error, right? But it's definitely between 25 and 30 meters or units per second that you're going to be falling on any planet. Well, this probably won't be the case on airless planets, or like planets with no atmosphere, right? Those have different, I guess, physics that have been assigned by the engine. But for any planet with some atmosphere, that's a regular planet, I guess this is how you would be falling. So I guess there it is. We have our answer. So we just found how fast you fall in No Man's Sky. And I know it's pretty sad. I was actually expecting real gravity physics in the game, but I guess that's a pretty difficult thing to do. It will be hard to like implement all these equations and relationships for a game of the scales. But I mean, one day we could get there, but it's definitely not today. Well, that's all I have for you. If you enjoyed this video, please leave a like and subscribe for more gaming videos that might interest you. Thank you for watching. See you next time.